let's look now at a stoichiometric problem. So finding or solving for a reactant in solution. This is a kind of a nice long problem here in Alex. I like it because it's something, an everyday example. So sodium hydrogen carbonate, or also known as baking soda, can be used to relieve acid indigestion. Acid indigestion is a burning sensation you get in your stomach when it contains too much hydrochloric acid. So some foods really generate a lot of stomach acid, and that stomach acid is hydrochloric acid. If you've got concentrated or strong hydrochloric acid in your stomach, that's what dissolves the food and helps, you know, break it down. You know, you hear people say, don't drink Coca-Cola or, you know, carbonated drinks because they contain acid. You can look on the side, it even says phosphoric acid. You know, if you pour that onto your sink, it'll clean the soap scum. You know, if you, you know, put it on meat, it'll like tear up the meat. Well, guess what? Your stomach will do that too. You throw up on some meat, it's going to tear up the meat. If you throw up on soap scum, it's going to clean it off. Your stomach has strong acid in it, so it's not anything to worry about there being a little bit of acid in your Coke. It's you put in there as a preservative. So drinking a glass of water containing dissolved sodium bicarbonate neutralizes excess HCl through this following reaction. So here you have this reaction, and you see that you have hydrochloric acid, the baking soda, making sodium chloride, which again, it's not harmful to the body, it makes water, and it makes CO2 gas. And that might be the problem. If you do this, then the gas is produced, and then you burp because it gets rid of the CO2. Okay, so you don't want to overdo this. So suppose the fluid in the stomach of a woman suffering from indigestion can be considered to be 50 mils of a 0.091 molar HCl solution. So we have a volume here, and a molarity. I mean, you can put ones on there, but we're not doing a dilution here, we're doing a reaction. And so it's asking, if we wanted to neutralize this HCl, how much or what mass of sodium bicarbonate would we need? Okay. And so this is a stoichiometry problem. And so we have that mass action table where you write out the balanced chemical equation across the top. You set up your columns, so each species has its own column. You have on the chemical change row, you have X's, like minus X's for the reactants and plus X's for the products. And you would put those coefficients in front of the X's, but all these coefficients happen to be 1. So this is a pretty easy equation in terms of our mass balance. We have 50 mils of the HCl, and we're asked how many grams of the sodium bicarbonate. So we're asking for the mass of another reactant. So notice this path does not have us going over here. In the past, we would have like the question mark would be over here somewhere. We wanted to see how much product was produced. But in this mass action table, you can do this in any different ways. Like if you start with the reactant, you can go over to the other reactant. If you start with a reactant, you can go over to the products. So it's still the same kind of ideas, the same kind of math. You're using molar masses, you're using concentrations, and you're using mole ratios. So how do we get out of these lab units and into the chemistry units? We use molarity. So right here, we would use that concentration. The 0.05 liters, which is 50 milliliters, times our concentration gives us the number of moles of HCl we have. So we've got to get out of milliliters of HCl and into moles. So we use the molarity to do that. And so coming down here, we have molarity. To get out of volume and into moles. And then we're talking about this being completely reactive. So we're going to take this all the way down to 0 moles. So both the acid and the bicarbonate are going to go to 0 moles. But the question is, if I need to use up or chew up 1 mole of acid, how many moles of bicarbonate I need? Well, they have the same coefficient, but we could still use that mole ratio. you know, going from moles of HCl to moles of bicarbonate, it's a 1-to-1 ratio. So these ones right here are tied to here. And also to the equation up here at the top. So you get those coefficients in the mole ratio from the balanced chemical equation. And so that means I need 4.5 times 10 to the minus 3 moles of bicarbonate. And then how do I know how many, and what would deliver that number of moles? The molar mass. And so to get back here, I use the molar mass. And that's easy to do. I go to the periodic table, I add up the mass of sodium, hydrogen, carbon, and 3 oxygens. That's 84 grams per mole. And so then that tells me I need 0.382 grams of sodium bicarbonate. So 1/3 of a gram roughly. So this is the point, I guess, for the whole day, is that you can use that molarity to get out of the lab units and into the chemistry units. And if we wanted to then convert it to something else, we could use it in other ways too, like concentration of sodium chloride or the concentration of CO2, or later next semester when you learn the gas laws, you could calculate the volume of the CO2 that's produced, okay, if you know the number of moles. Okay. And so we have some time to do that. So let's go ahead and do that. Let's see what volume of water are we going to have. So let's see how many mils of water we'll make. So how would we do that? What would I do to get over here to the right column? We can say I start with 0 mils of water, okay, which is 0 moles. But to get here, I just add X, right? 0 plus X gives me the number of moles. What is X? X is right here. If I went from this many moles down to 0 moles by subtracting X, then X equals this number. 4.55 times 10 to the minus 3. And so over here, for every one of these, I've got plus X. So I have 4.55 times 10 to the minus 3 moles of NaCl. I have 4.55 times 10 to the minus 3 moles of water. And I have 4.55 times 10 to the minus 3 moles of CO2. Because I started out with 0 of all of these, or at least it was listed as 0. That wasn't talked about. So we're just filling out the whole table, right? And so let's get down here to moles of water. How would I get to milliliters? Well, I can get to grams and I know the density, right? So let's go to grams. How many grams of water would I have? I would take this moles and I would divide, let's see, divide by the molar mass. And so we've got, let me start over here, 4.55 times 10 to the minus 3 moles of water. And I want moles to be on bottom, actually. So I said divide, I'm going to multiply by the molar mass. So oxygen is 16 grams per mole, and each hydrogen is 1. So I have 18 grams per mole. So 18 grams per mole for water. So 0.0819 grams of water. and 1 gram of water is equal to 1 milliliter. So I could take that and multiply by 1 milliliter per gram, and I end up with 0.0819 milliliters. So not a whole lot of water, but we could calculate how much. And that's the point of this table. If you know how to get from square to square in this table, you can answer every question that I can ask you.